Right, okay. So new topic for today. We're doing some kind of geometry and physics applications, as of course y'all noticed recently. But on we go. The next one is called the Theorem of Pappus, sometimes called the first Theorem of Pappus. There's a second one. We'll talk about that later. I've always thought this was an awkward construction, Theorem of Pappus. Why don't they just say Pappus's theorem? And my best theory on why they don't say Pappus's theorem is because then someone would have to decide if it's apostrophe or apostrophe s, and the rules on that are weird, and everyone has strong feelings about it, but nobody really wants to argue about it because no one's really 100% sure they're right. So it avoids the problem very nicely to say Theorem of Pappus. Okay. We're going to have the same problem with Gauss's theorem and Stokes's theorem later on in the course, but anyway. Okay, so here's the big idea. It's really a very clever idea. But suppose you have a plane, and suppose you have a line in that plane, and then further suppose that you have an area in the plane entirely on one side of the line. Let's just say. And the question comes up of, okay, I want to take that area and I want to rotate it around, right, to make a volume. And this gets real hard to do a decent job. See, it's just so hard to, anyway, you make a volume, right? And you want to compute that volume. Now, y'all have seen some problems kind of like this, volumes of rotation, right, in single variable calculus classes. So this is different in the sense that it could be any plane, and it could be any line in that plane. But nevertheless, if you set up your axes the right way, there are some cases of single variable approaches that could work for problems like this. But let's just pretend we didn't know that temporarily. And a neat observation to make. And this is just, you don't have to do this, but this is super clever. When you take a single variable approach on these problems, what they tend to do is, as stated, take the area, rotate the area first, and then slice up the rotated volume. Right? And the observation I'm going to start with is, you could just do it the other way. You can take the area, slice up the area itself. Forget about the volume. Oh, sorry. Again with my elbow. Slice up the area itself. Look at each little piece of area. Right? Rotate just that little piece of area to make an onion ring. Right? And I'll observe, if you were to do that for each one of the little pieces of area and add up the volumes of all those little onion rings, you would get the volume in question. Right? So that's not a single variable calculus point of view, right? We are literally slicing up area into little pieces of area, and you just don't do that in single variable calculus classes. But anyway, we're going to take that approach here and see what comes out of it. And so here's a little piece of area. Right? We'll call that dA, and we'll say that little piece of area is a certain distance r away from the line that we're rotating around, and thus it travels a certain distance. Oh, let me do that with a pencil. It travels a certain distance, which of course is 2 pi r. Right? Circumference of a circle. Right? And in doing so, we generate a certain amount of volume. And I'll call dV. And I'm just going to make the observation that there's a formula for dV. Now, y'all may have seen arguments like this before, but what we've got is, it's like, again, sort of like an onion ring. Imagine that you tear an onion ring and then just kind of straighten out the onion ring. Right? It's going to turn into a little rectangular box, sort of a long, skinny rectangular box kind of a thing. Maybe it's easier to think of if you think of it as a rubber band, right? Unstretched, of course, rubber band. So the area times the length of that box, which of course is the circumference of that circle, tells you that that volume. So let's see here. Let's get back to the colors. So circumference, aka length, which is 2 pi r, times area, dA. And that's the formula for the for that little piece of volume. And then, as we observed before, the total volume, right? The total volume is the sum of the little pieces of volume. These little pieces of volumes we just wrote down, 2 pi r dA, and there you go. You have yourself a double integral that will compute the volume of that rotated solid. So that's the big idea. Now, this is not Pappas's theorem. This is sort of the double integral approach to computing the volume, and Pappas's theorem is a clever move that comes after this. Yeah.
This is kind of off topic, so I didn't ask. But
Okay.
is there like a relationship between the fact that pi r squared, or between the fact that the circumference is the derivative?
Yeah, there is, and yeah, it is a little off topic, and ask me in office hours, but yeah, there's a lovely point of view on that, totally. Yeah. It's a great question. Yeah. Okay, yeah, so here's where it gets really slick. Here's the slick move that I guess Pappas must have come up with. 2 slick moves. First slick move is to take this formula and then multiply and divide by A for no apparent reason. It's slick because there's no clear reason why we'd want to do that, but nice things are going to happen as a result. So I think it's uncontroversial. If you multiply and divide by the same thing, no problem. Okay, here's the really slick move. What we're going to do now is focus our attention on this integral here. All right? And now, in order to make sense out of this, I'm going to come back over here to this picture, and I'm going to set up a new axis system. I'm going to call this the r-axis, and I'm going to call this the s-axis. Not that it matters. And now, just pretend that we were using r and s as our axes instead of x and y and z and stuff, right? But just look at the r-s axis system. Notice that what we call r here as, the distance from the axis, the distance from the line L, well, now that's the distance from the s-axis. That is literally the r coordinate of that location, right? So I could interpret this r not as a distance, but as a coordinate. That's the r coordinate of wherever you might happen to be. And with that point of view in mind, notice then that this integral is literally computing the r coordinate of the centroid of our original area. Keep in mind we've got some area over here. We're doing a double integral over that area. That's our domain for our double integral. This expression that I have in green is literally the r coordinate of the centroid of that yellow area that we started with. And another way to say that is r coordinate of something means, remember we already talked about, that's the distance from that centroid. Let me put it, that's centroid in orange. Let's say the centroid is that point. That's the distance from the centroid to this L line, to the other axis. So that distance is r bar. So in what we have in green here, this integral is the distance from the centroid to the line that you're rotating around. So the real slick point of view. So this allows us to we're seconds away from getting to Pappas's theorem, and that is to observe that 2 pi r bar, which is what we're looking at, is the distance traveled by the centroid. When you rotate that whole thing around, 2 pi times that sort of radial distance gives you the circumference of the circle that centroid makes, or otherwise known as the distance traveled by that centroid. And there you go. Here's Pappas's theorem. Pappas's theorem says that the volume is the area times the distance traveled by the centroid. Very, very cool theorem. What's nice about it is that two things that are both computed by an ugly integral are related to each other without having to actually crank out and compute the ugly integral. Right? So let me highlight in that way. So I guess I'll keep the theorem highlighted. Let me clear my junk. The ugly integral is this integral. That's that would be a pain to compute. And what we're observing is that, this connects to it, and this connects to it, and therefore they are equal to each other. So if you're interested if you want to compute volume, cool. If you can just observe how much distance is traveled by the centroid, multiply by the area, then sweet. And you just computed something that otherwise would involve a double integral, but we're computing it without a double integral. And we can also go the other way. Give me 2 seconds. We can also go the other way. If you want to know where the centroid is, right? But if for whatever reason, if you should happen to already know the volume, and if you already know that area, then Pappas' theorem, again, allows you to compute something that otherwise would involve an integral just by looking at other geometric objects. Yeah?
How is this different from like the single variable approach you were talking about earlier? Because aren't you still calculating the area?
Well, yeah, but the whole idea is if this is already convenient. So if you should happen to already know the area. Like barnyard variety formulas, if your area is a circle or a disk, right, then you don't have to do an integral, you just know it. That's kind of the point, yeah. So let me show you an example. So let's suppose we want to compute the amount of volume that you get when you take this triangle, right? We're going to rotate that triangle around that line, and of course notice that generates a volume that's really hard to draw a picture of, right? But you get this volume back here, the volume of the kind of the, what is that, the golf tee kind of looking thing? I don't know what that is. It's a really weird little shot glass, maybe. I don't know. You want to compute that volume of what you get when you rotate the triangle around the purple line. Well, good news. I already know what the area is. That area, real easy to compute. Barnyard variety geometric figure, right? High school geometry formula. The centroid, no problem. Wrong color. Here's the line that we're rotating around. The centroid, no sweat, is clearly right there. Easy. You compute the centroid. So the distance traveled by the centroid becomes the distance from the centroid to the axis is easy to identify. Multiply by 2 pi. Excuse me. To get the distance traveled by the bad drawing. Distance traveled by the centroid, 2 pi there. And bam, there's your volume. And your volume is that product, which turns out to be 2 pi. So no double integral required. Very slick move. Right? Without Pappas' theorem, now there's different ways you could approach this. You could say, well, I'm going to slice this that way, and I'm going to use the washers approach from single variable calculus. Or you can do the move that everyone tends to be scared of in single variable calculus, which is to use shells. Y'all remember shells? Students tend to not like it. But anyway, you could use the shells approach, or you could use the double integral point of view that I was pushing earlier, which is to say, look, each little piece of area makes a little onion ring, and you could do a double integral of onion rings, right? And that would do it as well. But why do any of those? Pappas' theorem crushes. Yeah.
Do you still want us to show that it would be done by a double integral, and then just say?
If you're using Pappas' theorem, the whole point is to avoid the double integral has served its purpose, and therefore you don't have to do it anymore. Here's another example. This goes the other way. Here, suppose you are rotating a semidisk, right, like so, rotating that semidisk around this line, and no geometric challenge to see what happens when you rotate a semidisk around that line. You're going to get a sphere, or a ball, ball. Okay. That's another math semantics thing. Sphere means the surface, just the surface. If you want to talk about the solid enclosed by the sphere, that solid is called a ball. Okay. Well, in this case, where the centroid is unclear. The centroid of that disk, right? We went to quite a bit of trouble to compute that previously, and so that y coordinate of the centroid was trouble. But barnyard variety geometric formula tells me that what the volume is, and likewise the those are all standard pat things, and then just solve for your R bar, and you get the exact same formula that we got at great inconvenience the other day, that the y-coordinate of the centroid is that. So no double integral required. Very slick move. Okay. All right. So, there's another version of this. Is sort of they call this the second theorem of Pappus. It's the same argument, just applied in a different setting. Instead of rotating an area, suppose you're rotating a piece of curve around a line, and notice that when you rotate a curve around a line, you get an area. And so, what's the relationship between perhaps the length of the curve and the area, and how do you compute that area? Right? Now, I'm not going to go through this argument because this argument involves something called a line integral that we haven't defined yet, and there's no need for that. But what I want to point to is it's really kind of morally equivalent in the sense that you just notice that each little piece of curve makes a kind of circular ribbon kind of like thing, right? Maybe this would be better described as an onion ring. It's got that flat kind of feature that onion rings have, right? But anyway, that little piece of area, you can talk about adding up all those little pieces of area over the entire curve. And again, it gets weird because we end up with something called a line integral, and we haven't defined that, and let's not worry about it. But the punchline is, morally equivalent argument tells you that the area, overall area, is the length of the curve times the distance traveled by the centroid. So very familiar punchline and similar applications. So here's a nice application. Suppose you have the upper semicircle. Now I emphasize, talking about the semicircle, this is a curve. It's like think of a piece of wire stretched over there like that. Right? I am not talking about the disk. That's a different thing. Right, a disk is a piece of area, not what we're talking about. We're talking about the semicircle itself, just that curve. And no surprise, these are very, very different geometric objects. They do not have the same centroid. Right? I mean, why would they? That would be pretty darn weird, in fact, if they just coincided. In fact, anyway, the point is they don't have the same centroid. So if we want to compute the y-coordinate of the centroid, you could make a symmetry argument for the x-coordinate, but the y-coordinate, again, is a problem. We cite this other version of the of Pappas's theorem, and the y-coordinate of the centroid, right there, we can just relate it to the length, which is super easy to compute by high school results, and then the area of the sphere, which is another high school result. If you were to look at the area of that sphere, 4 pi a squared, old news. So the point is, all those things except for R bar, solve for R bar, and there you go, and here's what the answer ends up being. So another nice application. Everybody okay? Okay, so now some physics. So there's this thing called moment of inertia. A lot of y'all have probably not heard of moment of inertia before, or maybe you've heard the term but you don't know what it is, or maybe you saw it in a physics class and I told you what it is but you never understood why. I think very few students in this course have probably got a strong, comfortable idea of what moment of inertia is. So the first thing I want to do, and this is just a little bit of physics, but this is physics that is really an excuse to do some math, some important math, 212 math. So here's the big idea. I think a lot of y'all probably do know about this thing called kinetic energy, 1/2 mv squared. Very important thing in physics. Long discussion there, but this formula assumes that all the mass is moving with the same velocity, right? You got a thing and it's moving. Well, the whole chunk is moving, and of course every part of that chunk is moving with the same velocity. Okay, so we're going to consider a different story. Let's suppose that instead of mass moving with a constant velocity, let's suppose instead that we have a chunk of mass, and we're going to call this a two-dimensional, sheet of mass. And let's suppose that that is rotating around an axis like this. Right? Rotating around an axis. Well, now at this point, notice not all the mass is moving at the same velocity. This little piece right there makes it around one rotation. That's a certain amount of distance, right? In the same amount of time that this chunk over here makes it around one rotation, which is a much larger distance. So the piece moving around the blue path is moving faster. It has a higher speed. The green one has a lower speed. So this mass is not, you cannot use this formula. What velocity do you plug in? The velocity of the outside piece or the velocity of the inside piece, or what's the deal there? Right? So it's just, this old formula for kinetic energy just doesn't work. So big idea is let's use a Riemann sum and add up energy. Right? But before I get into that, a couple of quick reminders. Now these are old geometry facts, but in the same way that a distance of arc around a circle is the radius times the angle, right? Likewise, the speed is the radius times what we call the angular speed. It's the same thing, just divide by time, right? Distance equals radius times angle. Distance per unit time equals radius times angle per unit time. Okay. All right. So this thing here, omega, this is what we call angular velocity. It's just angle per unit time. How many radians per second is this thing rotating at? Okay. All right. Now let's compute kinetic energy in this circumstance. Again, this is just an excuse to use a Riemann sum. Again, that's what this section of the course is all about: is Riemann sums and all the good stuff you can do with them. Right? So this is a nice example. If you want to compute the total kinetic energy of, this lumpy thing here rotating around that line, we're going to break it up and look at one chunk at a time. Let's talk about that little chunk. How much kinetic energy does that little chunk have? Well, the kinetic energy of that chunk, I'm going to say it's 1/2 mv squared, right? That's a little chunk. That little chunk is pretty much all the same distance from the axis. It's pretty much all moving with the same velocity. And good old formula for kinetic energy is 1/2 mass velocity squared, right? So that's just basic, high school physics. And now that we have that little chunk written down, we can talk about adding up over the entire thing, right? The double integral, adding up over all the little chunks gives us then the total amount of kinetic energy. And having done that, now it's just a matter of doing some algebra, moving algebra around. So I'm going to take this v squared, rewrite it as omega squared r squared. V is, in fact, omega r. And now I'm going to take the omega squared, and I'm going to pop it outside of the integral. And then I'm going to take this 1/2, this is all perfectly legal, and I'm going to pop it outside of the integral as well. And notice all that's left then is this. And so kind of a nice formula for kinetic energy. Kinetic energy is 1/2 times something squared, right? That's got that same, it rolls off the tongue the same way as 1/2 mv squared. Even better, this thing that's being squared, just like the old formula, this is angular velocity compared to linear velocity. This is an angular analog of velocity. So this is really, on the sort of, superficially, in terms of just eye smack, it looks a lot like the original formula for kinetic energy. And with that in mind, so thinking of this as kind of an angular version of velocity, likewise, we're going to interpret this thing here that's sitting in the same place that m is as being an angular analog of mass. In this kind of 1/2 something times something squared kind of structure, this thing plays the role of mass. That's why it's interesting, right? Very often when stuff is rotating, angular velocity is what you know. So being able to write kinetic energy in terms of angular velocity, very valuable. And if you want to be able to write kinetic energy in terms of angular velocity, the other element of that story is this thing. And so this thing is intrinsically interesting. We give it a name. We call it moment of inertia. We use this letter I for it, I for inertia. That's what moment of inertia is, and that's why we care about it. It's an angular analog of mass in energy computations. So, okay, all right. Thus ends the physics. Right? But again, do note that the big foot in the door on this physics was rewriting kinetic energy as an integral, namely rewriting kinetic energy as a Riemann sum. So the big, who gets the credit for this argument going through? Riemann sums. This is another application of Riemann sums. Okay. Okay, so this is an object. So for those of you engineers, you're going to be computing moment of inertia a lot. If you're not an engineer, well, you are a Math 212 student, so you're going to be computing this thing a lot. All right, so heads up. This is a good formula to memorize. Make sure to memorize this formula, integral r squared dm. Just know it. Okay. All right. One thing to talk about, though, is let's talk about this r. Keep in mind r was, well, it was the distance to the axis of rotation. I want to point out that there's lots of different axes of rotation in the world. Sometimes stuff is rotating this way, sometimes it's rotating that way, sometimes it's rotating that, whatever. There's lots of different axes. And so how you compute R is different in all of those scenarios. So please don't memorize a formula for R. That makes no sense at all. There's too many different versions, right? If you memorize one version and then try to apply that to a different scenario that's incompatible, you're going to get a dramatically wrong answer, right? So it just doesn't make any sense. So don't do it, right? What you want to do to understand R is just think about the various different scenarios, understand the picture, and then just interpret accordingly, right? So, for example, if you're rotating around the z-axis, if your area is sitting inside of the xy plane, right, looking at a little piece of area in the xy plane, well, how do we compute the distance from a location in the xy plane to the z-axis? And no problem, right? You can easily see that closest point on the z-axis is going to be the origin, and the distance to the origin, Pappus formula. Right? So now again, don't memorize that formula. Right? Understand how the argument puts together, and then deduce the formula every time you need it. Okay. Likewise, let's suppose you're rotating around the x-axis, and you've got that, let's say, same piece of area there, and you want to talk about, okay, for a little chunk inside of there, how do you compute the distance then? Well, okay, very importantly now, the closest point, if we talk about the distance from that point to the axis, it's not going to the origin anymore. Now the closest point is drop down straight over, perpendicular to the x-axis. It's parallel to the y-axis, and check it out. It's, I'm going to call it the y-coordinate. Now, of course, it's the absolute value of the y-coordinate, because if it were on the other side if we're on the negative y side of the x-axis, the y-coordinate would be negative, but distances are always positive. So here, anyway, let's just say absolute value of y. But importantly, it's not square root of x squared plus y squared. If you use this formula, you're dramatically wrong. So don't memorize. Understand the picture, see the picture, infer from the picture. Okay. Various different versions of this. One last one I'll do real quick. Sometimes the line that you're rotating around might not be an axis, right? It might be that you're rotating around some other line, let's say parallel to an axis. And by the way, there's a million different, so you don't need to worry about rotating around that line. We're not going to do any of those kinds of things in this course. But rotating around that line, well, any given point that you're interested in, right, its distance to this axis, draw a picture of what that distance is and infer from the picture. And look, it's just not equal to absolute value of x. It's not the x-coordinate, right? It looks like I actually just, I just bolded over the answer. It depends on this value of a. It depends on where the line is. And it's just going to be x minus a, absolute value, of course. Okay, so see the picture, infer what r is from the picture. Please don't memorize. Okay, right. Okay, quick example. Let's compute the moment of inertia. We've got this area here that's between that curve and the x-axis for these values of x. So here it is. Right there's our area. There's no density given, so we're computing the moment of inertia just of this geometric region. So again, we assume that the density is 1. If density had been given, then density would factor into the integral. But again, as it is, dm is just area. Mass is just area when the density is 1. Okay. And now, again, on the picture, some little piece of that area. If I'm rotating around the x-axis, I can see that the distance to the axis in question is just, well, it's y. Right there in the picture. Yeah. And there you have an integral, and here's a double integral to compute, and off you go. And so section 14.3 methods, and you can compute that integral. So everything down here is just yada yada yada. Yep.
Why couldn't you say r equals x?
Because it isn't. Right. Look at the picture. Right. So x is that distance. Sorry.
Okay. Oh, so
yeah.
Could x couldn't be like the curve?
I'm sorry, I don't understand.
Like, I just wait. Is the picture like? Are you given the picture?
You're given the statement of the question here, and from the statement of the question, everything that's stated in the question. Yeah. It's because we're going around the x-axis. Yeah. That's right. Yeah. Yep. Yes.
So you did dA because you're finding the moment of inertia of the entire area as opposed to just one mass.
Yeah. So the question is that we've got area that's spread out over this entire region. And see, that's what makes it a hard problem, right? If you just had a single point, right, then why would we talk about angular anything? Everything's moving at the same velocity at that point. You would just use 1/2 mv squared. Yeah. So yeah, that's right. Okay. Okie dokie. There's one other thing I want to point to in this example. A lot of students have kind of forgotten how to do integrals. And a lot of y'all may have forgotten how to integrate sine cubed, because it's one of those, you just got to remember all the little tricks. There's a bunch of different kinds of integrals, and you just got to remember all the moves. And you got to not only remember what the moves are, not only remember how to use each individual move, but be really good at, in context, being able to identify which move should I do, be able to do the puzzle aspect, the sort of the diagnosis aspect of the integration, be able to, get the job done on doing integrals. Math is a very vertical thing, right? When we're done with one topic, you don't just throw it away, never to be seen again, and move on to the next topic. It builds, right? So being able to do single variable integrals is unavoidably critical in being able to do multivariable calculus. So make sure that you're good at your single variable integrals. If you're a little rusty, you want to brush up. Definitely. So make sure to do that. By the way, for FYI, so for those of you who are engineers, about 20 years ago or so, the engineering school actually came to us, the math department, and said, "Hey, by the way, what's up with how come our junior engineering majors can't do single variable integrals anymore? What's going on there?" And what they eventually realized is that there were some instructors who were kind of like, don't worry about the single variable integral portion. Yeah, whatever. I know y'all know how to do that, right? And the point is this was allowing students to get rusty, and then in fact to not be able to do single variable integrals anymore. So as a result, the engineering school asked us explicitly, don't do that, right? We need our students to be able to actually do integrals. We're building stuff here. We need to be able to work it out to an actual answer. We need to know how long to cut the metal rod, right? Where do we cut, right? It's not good enough to just have the answer down to this. They need to know that. Okay, all right. So You got to make sure that you can do that kind of thing. Okay. Super duper quick. There is this other thing called radius of gyration. It relates to moment of inertia by way of this formula. It has a cool physics interpretation, and this is not a physics class. So if you're curious about that, there's some discussion in the book. You can come ask me in office hours. For the moment, I'll say, look, this is a really short formula. It'd be really easy to memorize this formula. Please go ahead and memorize that formula. I'm not very interested in it, but right before the final exam, maybe memorize that formula, just in case somebody's got a strong feeling about, I want my students to be able to compute radius of gyration. I don't think it's likely, but anyway, there it is. Just know the formula. Okay, so on to triple integrals. This is where things start to get really geometric. Quite a bit more geometric than they have been, and they've already been pretty geometric recently, haven't they? Right? So this is going to get unavoidably three-dimensional geometric. We're going to be drawing lots of pictures three-dimensionally. If you're not good at drawing three-dimensional pictures, this is the time to get good at drawing three-dimensional pictures because they're unavoidably essential in this kind of work. Again, I'll remind you, I have lengthy discussions on my YouTube channel in the miscellaneous topics section. There's two videos called Drawing. I think they're called Drawing 1 and Drawing 2. Right? So if you're not good at drawing three-dimensionally, those are worth your time, I think. And then, of course, practice. Okay. So, we want to define something called a triple integral. We did double integrals. Why not triple integrals? And reasonable question, if we write down triple integrals, what's our starting point for that, right? What should be our motivating problem? So when we were doing single variable integrals, this was our motivating problem. We want to compute the area under a curve. Why we want to compute the area under a curve never, came up very much. But anyway, we decided we want to compute the area under a curve, and so we motivated this construction called a Riemann sum. And then, as and I've talked about this before, but as kind of an afterthought, students it's pointed out that, and by the way, you can also compute these kinds of things, which actually end up being honestly more important than area in the first place. Nevertheless, we had a motivating example that gave us this idea of a Riemann sum. Okay. Double integrals. Very first way we were thinking of double integrals, again, we were thinking about, we're looking at a graph and thinking about how much is there under the graph. Now, in this case, of course, it's volume under the graph because it's the volume under a surface because the dimensions are all higher. Right? But anyway, that motivated this construction. And then, of course, there's other examples. Now, I've hit harder here. I was your probably first resource on double integrals, and so I've hit harder all of the different applications that there are there and tried to generally sort of discourage this point of view on double integrals because this is very narrow, nothing else. All right, so these are the kinds of questions I want to ask. Now, suppose I want to take the next step and go on to talking about triple integrals. Right? So let's make a couple of scratch notes on here. This is a one parameter integral, and here is a one-dimensional picture that we can use to think about it, and then here is a two-dimensional picture that you can use to think about it. Right? Here is a double integral, two-index integral. Here is a two-dimensional picture that you can use to think about it. Here then also is a three-dimensional picture that you can use to think about it. Now, pros and cons. A big pro of this point of view is that we're using an extra dimension. We've got an extra dimension that we can see. Right? I can see what this integrand is. This integrand is height. Right? This integrand is height. I can see it on the picture. I can't see density on this picture. I can say density, and I can say use your imagination. You all remember dense things, right? Things that seem heavy for their size, right? I mean, so it's something you can talk about, physically. You can relate to it, but you can't see it. Right? Okay. So that is kind of an argument in favor of this point of view. But, of course, not hard to see where this is going. Let's talk about what happens when we try to take the next step. If we try to extend to triple integrals, I made a hard to clean up mess here. Where do we go? Right, if I want to talk about a triple integral, well, if I go down this point of view, I get a three-dimensional picture. But if I go down and take this point of view, follow that pattern, I get a four-dimensional picture. Correction, I would need a four-dimensional picture, and of course I can't. Right? Everybody see the problem? So there's a point. So here, the problem, as I'm going to present it here, is that while it's fun to spend, right? It's cool things you can do when you spend stuff that you've got. And if you've got a lot of dimensions, you're just throwing those dimensions around like, hey, look, we can see the integrand in nice geometrically satisfying ways. And yeah, sure, you spend your dimensions and you get a return from that. Well, we were not being dimensionally frugal. We are now over our dimensional budget. We just can't afford to take that point of view with triple integrals, right? So that's a problem, right? So now, how does this affect y'all? The way it affects y'all is here's the dead end that a lot of students run into at this stage. Is a lot of students are like, okay, I'm going to think about single variable integrals this way, and I'm going to think about double integrals this way, and then I'm going to think about triple integrals this way. And what you've got is a disconnect, right? For one thing, students are using three-dimensional pictures to understand two very different kinds of integrals. That's confusing. I'm just saying, right? Okay, so let's add this to the list of reasons that I think graphs are overrated, right? So for one thing, it's very important to understand that these pictures are not the definitions of integrals. Integrals are not defined as area under the curve or volume under the surface. That is not the definition. That's important for application reasons. It's important that the definition of an integral is Riemann sums. And so let's call this, dis number one on the graph point of view, right? But the second gripe that I have, the second counter argument that I can make about the graph point of view is the graph point of view leads you into trouble, whereas this mass point of view leads you to somewhere where you got somewhere to go. Right? So anyway, for your consideration, I strongly encourage, try to wean yourself away from thinking about integrals in terms of graphs. It's problematic, right? And try to wean yourself toward thinking about, even in the case of single variable integrals, try to think of single variable integrals as accumulations over one-dimensional domains. You don't need to think about area. Don't think about area. This is heading you in the wrong direction. Think about double integrals as accumulations over two-dimensional domains. Right? And then, following the pattern, think about triple integrals simply as accumulations of stuff. Whatever it is, mass maybe is a nice sort of viscerally relatable metaphor, right? Accumulations over three-dimensional regions, three-dimensional domains. That's all it is. Okay. All right. Right. Okay. So, good news. In fact, this point of view here is actually pretty darn relatable. In fact, this notion of density being mass per unit volume, that's the notion of density we're all sort of initially accustomed to in the first place, right? We had to kind of stretch our imaginations to think about density as mass per unit area. That was weird, right? And then mass per unit length. That was a little weird and unrelatable. And I'm talking about chains from the hardware store, right? Mass per unit volume. That's what they told me in 8th grade. Density was supposed to be. Okay, so with all that being said, here's your definition of a triple integral. It's just a Riemann sum. We're just taking a piece of volume, we're chopping it up into little pieces of volume, we're adding up over all of those little pieces of volume, which now, by the way, of course, go in 3 different directions, right? For each little piece of volume, for reasons appropriate to the application, I'm going to multiply some integrand times the volume. Again, the easy one to visualize is density, because density, mass per unit volume, times volume gives you mass. You can think here as we are accumulating pieces of mass if this is mass per unit volume, right? Very natural construction. We're just chop it up, add it up. Just like we did for double integrals, just like we did for single variable integrals. The notation is actually pretty darn plausible, right? Who wouldn't have made that choice? Right? And then likewise, there's 3 different indices that we're adding up over, so 3 different integral symbols. Seems pretty reasonable. Okay, I've already made the observation. Please don't focus on the graph point of view, area under a graph, volume under a graph. Again, that's instead, you want to think about the mass application as your motivating example. We've talked about different kinds of densities, and I'll just point out, by the way, that density doesn't have to mean mass per unit volume. It could mean amount of a pollutant per unit volume, and so you could talk about that pollution density, or as we sometimes call it, concentration. But it's still stuff per unit volume. More generally, stuff per unit size. Right? Remember, if you're talking about population, we tend to think of population as stuff per unit area. Okay. All right. How are we doing on time here? Okay, I have 15 seconds. All right. Just a little bit of foreshadowing. Being real flexible about how you think about density is actually going to be hugely important when we get into chapter 15. The big chapter that everyone's scared of, the rep that Math 212 has largely comes from chapter 15. That's where the calculus gets really really geometrically challenging. And a big point of view that helps in understanding that material is to have a very flexible interpretation of density. And there are going to be geometric densities that we're going to talk about. Not physical stuff per unit volume, but we're going to be thinking instead about geometric quantities. I'm going to be real vague about this, but there are certain geometric objects that you want to know how much of that geometric thing per unit volume is there. And details to come later. But what we can do now to prepare for that is get real flexible about how you think about densities. Okay, good place to stop for today. Y'all have a great weekend. Stay warm and dry and safe.